Well, we saved the best for last, and that is graphing exponentials. I know you all love graphing as much as I do, I'm sure, right? So let's take a peek at a base graph of an exponential, and then using that knowledge, it will be very easy to extend our understanding of transformations to different graphs of exponentials. So I'm just going to pick on a friendly base. So let's just deal with graphing y equals, how about we do 2 to the power of x, right? We could really pick any base that's a non-zero positive number, right? But let's just pick on 2. And just like we would do with any other new type of function that we learn to graph, let's just make a table of values so that we can understand the basic shape of this graph pretty nicely. We did talk about the fact that the domain of exponentials are all reals. So for that reason, you can really pick anything you'd like. I like to pick a handful of negatives, 0, and then positives. So that's kind of my typical approach for an exponential, at least when it's a base graph. From those choices, we can easily find the corresponding y just by understanding that we're plugging these x's in as the exponent. So if I take negative 2 and use that as the power on 2, what is 2 to the power of negative 2? Well, I'll show some steps of how to do it by hand. Of course, you can use a calculator, but we do know that when you have a negative power, it's the same as pushing the term to the denominator and making the power positive. So when I see 2 to the negative 2 by hand, I understand it better as 1 over 2 squared. And 2 squared, is 4, so I will get back 1/4. Or if you prefer decimals, 0.25. Okay, I'll keep showing my work for what it's worth. The next value I'm going to stick in will be negative 1. So if I stick in negative 1 as the power, 2 to the power of negative 1 is the same as 1 over 2 to the first, and 2 to the first is just 2. So there we'll get back a half, or 0.5 if you're more of a decimal fan. All right, keep plodding along, plug in 0. 2 to the power of 0. Anything to the power of 0 is just 1. So we get back a y value of 1. And then these last two values are going to be the most straightforward. So we kind of started off with the harder values, but the last ones say plug in 1. So 2 to the first is just 2. And then our last input of x is 2. So 2 squared is just 4. So those aren't too bad once we get into the positive exponents. If I plot those 5 points we just found, we should come up with a pretty decent shape of our exponential curve. We should find that it reflects a domain of all reals and a range of 0 to infinity. So I'll go ahead and plug these points in. And we'll just do our best to create a decent sketch. So when x is negative 2, the y value is 1/4, so it's just barely popping off the x-axis there. This again is a sketch, so it's not perfect. When x is negative 1, I go just a tad bit higher to 1/2. When x is 0, I'm at the y value of 1, so I'm at an actual tick mark there on my scale. When x is 1, we'll keep increasing to a y value of 2. And when x is 2, our y value is up to 4. So I like 5 points because exponentials are not linear, right? For a linear function, 2 points is adequate, but exponentials are more curved. So by plotting 5 points, I have a really good feel of the curve here. So on the left side of the graph, we are approaching but not touching the horizontal asymptote. And then on the right side, this graph is just going to continue growing infinitely in that direction. So that would be a pretty darn good sketch of y equals 2 to the power of x. Let me just again state the domain, the range, and the y-intercept for that one. So the domain for all exponentials, this is your freebie here, is negative infinity to infinity. The range will depend on the actual equation. So sometimes your graph could get shifted vertically. That would impact the range. Sometimes your graph could get reflected about the x-axis, and that could also shift the range. But here, the range is just from 0 to infinity. So we have that horizontal asymptote at 0. And then the y-intercept is another value that we'll often talk about. And in an untransformed exponential, that intercept is just going to be at 0, 1, because anything to the power of 0 is 1. So the intercept on our graph here, just to make sure we all see it, is this point right there. Cool. So just with that knowledge, I would highly encourage you guys to jump into Desmos a little bit and explore what the transformations look like. But if I wrote a related equation, such as y equals 2 to the x plus 1, I would expect us to be able to say that it's the same graph we just plotted, but it's been shifted, right? How has this graph been shifted compared to the example we just did? What does this plus 1 do to your graph? And I think without too much trouble, we'll say this plus 1 at the end will shift the graph up by 1 unit. So all the points on the graph would bump up by 1 unit. Similarly, if I wrote you an equation like 2 to the power of x minus 3, I think you guys would be able to tell me that the minus 3 up there with the x is going to shift the graph. Any ideas on this one? Minus 3 would shift us right by 3 units. So our same understanding of transformations, specifically shifting the graph left, right, or up or down, all that we learned in the first units is still applicable here. So play around with Desmos a bit, and hopefully that starts making graphing feel pretty intuitive to you.